Welcome to the videos on pharmacology. I've done a lot of videos on pathology, and now I'm going to switch to more pharmacology, and we'll talk about how pharmacology is related to pathology. And I'll create playlists of pharmacology and playlists of pathology. And so pharmacology is the study of substances, drugs, chemicals, any substance in the body that interacts with living systems through chemical processes. And pharmacology has a specific interest in how these substances that interact with living systems bind to regulatory molecules that then activate or inhibit normal biological or physiological processes. So a drug is any substance that brings about a change in your normal physiology through chemical actions. So that's what a drug is. And in this first video, we'll talk a lot about just concepts and definitions, so that when we talk about certain principles, that we'll be kind of familiar with the terms. So there is agonists and antagonists when you talk about pharmacology and drugs or these substances. So what an agonist does is an agonist activates. So turns on, if you will. Turns on a switch or turns on a process. An antagonist is off or inhibits this process from happening. And then how this normally happens is through a receptor. And a receptor is, let's say this is a cell membrane here, and there's some kind of molecule or protein that sits inside this. This has some kind of receptor. As we've talked about in the pathology videos, this could be, this is all just amino acid sequences, and so there's going to be some kind of substance, a drug, a normal hormone that's going to come, and it's going to sit on this receptor. If it's an agonist, it will turn on this process, on. If it's an antagonist, it will inhibit this process or this molecule from functioning. So drugs interact with receptors. Drug interact with receptors through chemical forces or bonds. There's three major types. There's covalent, electrostatic, and hydrophobic. The actions of drugs on the body are termed pharmacodynamic processes. So how the actions of drugs affect the body, that's what you'll hear this word, pharmacodynamic processes. And so we're going to talk about some of these processes. So if you have a drug and you add it to a receptor, there's a lot of different ways that these pharmacodynamic processes can happen, and here are some examples. So a drug that gets added to a receptor, and then that creates a change, and then the drug receptor effector complex, and then there's an effect. So if there's a drug plus a receptor, then you get a drug receptor complex that could just go straight to that could then activate an effector molecule, and then you have an effect. So you can kind of see, like, if there is a membrane here and some kind of drug, so this is a drug, and then this comes onto the receptor. Well, so once they bind, then that process in and of itself can just create an effect. And that's in this situation. If you have a membrane and you have a drug, that's the drug receptor complex, and then that somehow activates an effector molecule, and then that now turns to an effect. So there's several different ways that these drugs can act on the body. So if you have a drug plus a receptor, well then that equals the drug receptor complex. Then there's another mechanism that activates a coupling molecule. So add another molecule in here in this kind of process. Then that affects an effector molecule, and then you have an effect. And so you can also have inhibition of metabolism of endogenous activator, which then leads to increased activator action on an effector molecule, and then you can have an increased effect. So there's several different ways that these drugs can interact with the body, and these are called pharmacodynamic processes. So the actions of the body on the drug are called pharmacokinetic processes. So pharmacodynamic processes is how the drug is acting on the body, and then pharmacokinetic processes are how the body is acting on the drug. And a couple more terms here. Drug affinity is the tendency of two substances to form strong or weak chemical bonds forming molecules or complexes. So drug affinity is the tendency of a drug and a receptor, or two drugs, or a receptor and a molecule, an effector molecule. The drug affinity is the tendency of two substances to kind of interact with each other. And then drug efficacy is the ability of the drug to produce the desired treatment or therapeutic effect. So drug affinity is a tendency of how well these two molecules want to work together, and drug efficacy is how effective is the drug, or what's the ability of the drug to produce the desired effect. So we have here a picture, and this hopefully this will kind of clear up a lot of the last slide. So the agonist right here, this molecule, so this is going to be a receptor here. So the agonist right here, it's going to bind to this receptor here, this part of the receptor, and it's going to turn it on. This is going to be on. So then this is going to follow this path. This is going to have an effect. So the competitive inhibitor, what this is going to do, this is an antagonist. What this is going to do, it's going to compete because it's kind of got this same shape here as this curve. It's going to compete for this binding site. So if this is, if I have 6 molecules of this and I have 6 molecules of this, and they both have the same kind of shape to fit into this receptor, they're going to compete for that. And this is an antagonist, so it's going to turn off. It's going to turn off this process, so there will be no effect if this competitor inhibitor binds here. You can also have an allosteric activator, which is a different molecule or a different binding site, different than the normal receptor. And you can have an allosteric inhibitor. And what this does is, if this purple molecule comes up here and binds here to this part right here, what that does is it makes a conformational change. And you hear that a lot. What is a conformational change? What it means is that through the chemistry and biochemical processes, if this allosteric inhibitor molecule comes and sits in this receptor, what it will do is it will change shape. It will change shape. So maybe like right here, instead of a circle here, it will maybe block this off. It will fill in this hole. And if it fills in this hole, then this agonist or this antagonist molecule can no longer bind, and so you'll never get an effect. And so, and another thing that's interesting about this is these log doses. So if you take the log of the dose of the molecule inside the blood or inside your body, and you compare that to the response, if you have A and C, so if this binds to here and this agonist binds, then you get the largest response because both of these are activating. So the allosteric activator kind of binds here, and maybe this guy's got a little bump here on his little surface here. Well, then the allosteric activator might put a little bump here, and so this guy will be able to bond to this receptor site much more efficiently and effectively, and maybe stronger too. And so that will create a greater response. And so that's why you see A and C have the best response. So then if you have A alone, if you have this agonist, and it comes in here and binds to this site here, then you have a certain response. And then if you have A and B, and you can kind of see that if you have equal amounts of A and B, you can, it kind of delays the response, but eventually it will get up to the same response as A. It just might take longer because these competitive inhibitors binding, and then it's coming off, and then the agonist takes a turn, and then this one takes a turn, so they kind of switch back and forth. But if you add more of a concentration, so this is more of a concentration of A, then that will overcome this competitor inhibitor because it's just probability, right? If I have 6 of these and 6 of these, if I increase the concentration by 100-fold or something, so then I have 600. I have 600 compared to 6. Well, then it's just probability that this agonist is going to bind to this site a lot more than the competitive inhibitor. So you can overcome this antagonist by increasing the concentration. And then if you have an A and D scenario where you have A and you have D, this allosteric inhibitor comes and it might bind to this site right here. Well, then that's going to cause a conformational change in this molecule where it's going to change shape, and the agonist won't bind to this receptor as much, and so you'll get a lower response. And in this picture it shows that the agonist still is able to bind, but there's some cases where this guy completely blocks it off, so you'll just get a flat line.